So everybody, I'd like to welcome you. Mark Stock is about to present on a project he's been working on. And then we're going to segue into the presentation by Chris Wan here on genomics and supercomputing. So, Mark?
I've got 5 minutes, so I'm going to summarize kind of what goes on in my mind all the time. I'm interested in computational physics, in algorithmic art, and all of this stems from using interacting automatons. I know that in AI or in genetic algorithms, you use these DNA strands. It doesn't matter where they are in space. But what I care about is things that are in space. And let's look at the values of fields in space. And there's two ways to look at that. One way is to pick a grid or some sort of pattern in space and fix values at those positions. Or the other way, called the Lagrangian method, is to have particles that flow around, and those particles carry values with them. I'm going to start with the Eulerian method, show you a few interacting automaton simulations from that, some of which you're already familiar with, and then I'll go into the Lagrangian one, and then I'll show you some pictures of some stuff that I do. So we know what this is. This is not an interacting automaton. This is you pick a point in space, run a formula, and it tells you if it's black or white. This is the Mandelbrot set. That's not what I'm talking about. I think this is boring, frankly. You can zoom in on that forever, fine, but it doesn't move. It doesn't do anything interesting. There's no... Well, the emergent patterns in this are only from the initial data string. What I'm interested in are things like this. This is, of course, this is Connor's Game of Life, and this is some sort of thing that shoots off deal. So this is a type of simulation where there are values at each point in space, integer indexed. The value is either 0 or 1, and a little algorithm figures out whether the next time step, that single square is 0 or 1. And the range on this is just 1 square. So 1 square for the next step only has to know what the 4 adjacent squares are doing to know where it's going to go next. So that's a very limited range automaton. This is a one-dimensional CA from Wolfram. This is the Rule 30 thing. This is just in one dimension even. This is even simpler than the last one. The little algorithm that says, how do we figure out what the color of this pixel is at the next time step based on the 3 pixels that are right over it. Very, very simple again, but you can start seeing some emergent behavior. This is the same, not the same thing, but this is a different rule in 3 dimensions. This is just, this is the activator inhibitor reaction. So there's just a simple formula that's algorithmic and arithmetic that tells whether the pixel is black or white at the next time step. This is kind of hard to see. This is kind of like a CA, but this is an erosion simulation. So if I fixed my gamma, you could see little rivers forming and other crap like that. This is a picture of BMW I took in Germany. This is diffusion. One thing that you can do with CA is diffusion. If you say that the value of each pixel equals the average of the values of the 4 pixels around it, and you update the time, you pretty much blur things. So that's what this does. The next step beyond that, instead of just diffusion, you do something called convection and diffusion. And a convection diffusion equation is the basis of fluid dynamics. So what I'm doing now is I'm saying that all bright colors are hot, they're going to start rising up, and the dark colors are cold, they're going to start falling. And this is just convection and diffusion. And what we get from this simply a cellular automaton simulation are these beautiful fluid dynamic forms. Lagrangian is the other way of doing things. Lagrangian says that we have elements in space. They can be particles, they can be triangles, they can be segments, they can be connected or not connected, and each of them influences the particles around them. For this one, this is a structural simulation of a crushing can. Each of these little cells, little squares, affects only the square next to it still. It has a little formula that figures out where it moves based on where its neighbors move. And when you solve this equation a lot, you get some very complicated behavior here. This is radiosity. This is kind of a different thing. This says that we're going to take our whole scene, kind of like this room here or this room in the picture here, and we're going to say that all the light that hits that, some of it's going to bounce back. If it's white, all of it will bounce back. If it's black, none of it will bounce back. But we need to look at all the little panels on the wall and how they interact with the other rectangular panels on the wall and how they share energy among them. And energy bounces around until it gets absorbed ultimately by everything. And that's called a radiosity solution. And that's why when you shine light in a white room, it bounces around, everything looks bright. Shine light in a dark room, you can't really see much. This is a simulation of that. This is something called smooth particle hydrodynamics. This is another fluid dynamic thing but it's fluid dynamics done with particles. So each particle affects the particles in a very small radius around it, and it pushes away. This is pretty much like a simulation of marbles, but not hard sphere contact, kind of like a soft contact. And if you customize the formulas that you use for these particle interaction formulas, you can get very realistic behavior of some very interesting physics. For example, bullets hitting armor, they actually melt and splat, and other weird things happen, weird physics go on. These formulas can capture some of that. This is the gravitational simulation. We all know that in gravity, you've got one mass over here, one mass over here, and they attract each other with a force equal to 1 over the distance squared. So that means that each mass attracts everything in the universe, and everything in the universe pulls on each mass. It's kind of a hard simulation to do, but that's what a lot of my work is. Not gravitation per se, but this is a gravitational simulation. This is the start of it. This is after a few time steps. So this is kind of back and forth here. This is like 20 or 30,000 particles. It would normally be an in-squared operation, but there are neat methods that we have to drop that down to in-log in or even order in. This is the same thing in 2 dimensions. It turns out that the gravitational code that we can use can also be used for electrodynamics, because electrons and positive negative charges react with a 1 over r squared potential also. So does swirl in fluid flow. This is vorticity. Each particle has a little rotation attached to it, and each rotation influences all the other particles to move. So when you do that, you get 2-dimensional fluid flow. You can do it in 3 dimensions too. This is what my company does. So this is 2 disks flopping back and forth. I thought I had like 7 frames here. So this is about 100,000 particles. And we can run this on parallel computers, and we can do all sorts of crazy shit with it. And what I do with all these codes is I make art with it. I've got about 7 pieces here. This is just lines in space that are vortex lines. Flow revolves around these lines and twists up and folds and spreads and does all sorts of crazy things. This is one of the images I made with that. This is an image where there's a fluid dynamic field and I just trace lines through it. This is for my research, for my PhD. This is a sheet of swirl. If you kind of think of the way that your hands go together when you clap, fluid on one side moves one way, fluid on the other moves another way. And if you can simulate a sheet of that, that sheet contorts and bends and folds and merges and makes funky shapes like this. This is more tracing streamlines through paths. This is the same geometry as that one, but just rendered differently as glass. These are some particles in space. I just picked them out and rendered them as triangles. And this is some stuff that was at the collision show at MIT earlier this year. That's my 5-minute welcome to interacting automatons. Are there any questions that last less than 2 minutes or 1 minute?
I have a question. So in terms of render deck, converting the raw geometry into the rendered image, what rendering program or?
I use a rendering program called Radiance to make my images, and that just takes 3-dimensional descriptions of scenes. So like cylinders, and this is just polygons in space over triangle mesh. This is just triangles in space with a different modeling surface attached to them.
About how long do these images take to produce in terms of rendering time?
I render my art at anywhere between 7,000 by 7,000 up to 50,000 by 50,000, and they take anywhere between a day and a month to render.
And if you wanted to do something closer to 640 by 480, or what I'm wondering about is, how close could you get to real time?
Not close. Ray tracing is not the way to do real time. The hacks that they've made and the corners that they've cut to do real time graphics in games are really terrific. Genius to put those together, and they can do, of course, high frame rates with reasonable looking graphics with very, very complex scenes. I can do complex scenes with actual realistic light into reflection, but that takes, extra hours per frame or minutes per frame, depending.
Are these still frames of animations that you render in that style, or is everything still framed as the final output?
Still frames are the final output, and that's what I only try to render. I've only done one animation, and it took just way, way, way too long.
Okay, so the month to do something is that 50,000 by 50,000?
That's that one frame, yes.
Wow.
That gigapixel frame. Thanks very much for your time.
Thank you.